Welcome back, folks, to another JLand Bio exclusive video focusing on physics. Yes, physics. I realize my name is JLand Bio. I'm teaching physics. Get over it. Today we are going to focus on something very, very important, and that is Newton's laws of motion. Sir Isaac Newton, a very important part of physics, born Christmas Day, 1642, died in 1727. Discovered a lot of important information about how forces, acceleration, and velocity all work. So we're going to dive into those today and look at how we can apply them to some of the concepts that we've already talked about, like vectors. So hopefully by the end of this video, you should be able to explain Newton's laws of motion, and then you should be able to apply them to vector physics concepts. So let's start off by talking about some of the important laws that Newton put forth. And Newton's first law describes how objects are affected by forces. Now, keep in mind that a force just simply a push or pull one way or another. Keep in mind that with forces, we also not only look at the magnitude or the strength of the force, but the direction in which the force actually goes. Newton's first law simply states that an object remains at rest as long as no net force acts upon it. Now, we do need to keep in mind that there are forces that are acting upon objects at rest. There's just no net force. An object at rest means that the forces that are being acted upon that particular object add up in terms of their vectors to a sum of zero. Also keep in mind that an object moving with a constant velocity continues to move in the same speed and in the same direction as long as there is no net force that is acting upon it. So simply put, an object at rest is going to remain at rest until an unbalanced force acts upon it. So for example, kicking a soccer ball. The object in motion will continue with the same speed and direction unless another force, such as the back of a soccer net, acts upon it. The back of the soccer net acts as a force going in the opposite direction in which the ball is traveling and therefore stops the ball. Now, most objects experience more than one force on it at a time, even objects at rest. Consider a plate that is sitting on a table. A plate that's sitting on a table exhibits a force on the table due to gravity. Obviously, things want to fall, but the table is actually also exhibiting a force acting back up upon the plate itself. That is why the plate does not move, is because the forces cancel each other out. The force downward towards gravity is actually acts upon the plate, while at the same time, the normal force acting up from the table to the plate is the same as gravity, which is why the book does not move. Now, if we slide the book across the table, then we've got a couple other forces that we need to take into consideration. The force being applied to the plate being pushed, as well as the friction force that the table is imparting on the plate as well. So when we look at net force, it's not just as simple as an object at rest has no forces on it whatsoever, but rather we need to consider a variety of different forces that are taking place simultaneously. So let's look at changing an object's motion. Objects don't just change motion on their own. There has to be some type of other force that goes into effect in order to change the object's motion. Now, on Earth, we have friction, which is the force of the contact of the surface of anything with the object that is in motion. We also need to take into consideration air resistance as well when we're looking at objects that are flowing through the air. Now, Newton's first law is also referred to as the law of inertia, and inertia is just simply the tendency of an object to resist changes in motion. So consider that you're in a car accident. That's very unfortunate, but you're wearing your seatbelt, which is a very fortunate situation. You know that when you brake really, really hard, your body tends to stay in motion until another force acts upon it, which is why you have a seatbelt on. That seatbelt acts as a force in the opposite direction to slow you down so that your head does not go through the windshield. That's a very, very good thing, especially when we're talking about car accidents. So consider a heavy anvil that hangs from a string attached to the ceiling. An identical string hangs from the bottom of the anvil. Which string breaks if you jerk the lower string down rapidly? Well, if the lower string is pulled down rapidly, the inertia of the massive anvil keeps it from responding very quickly. Since the anvil barely moves, the force in the lower string quickly becomes large. And as a result, the lower string breaks before the anvil has a chance to move. Pulling slowly on the lower string, however, would cause the upper string to break instead. So if we were to jerk the string very rapidly downward, we would actually break the lower string rather than the upper string due to the inertia of the massive anvil. The inertia of the massive anvil, because it's so large, keeps it from responding relatively quickly. So let's consider Newton's second law, which basically states that acceleration of an object depends on the force and the mass. Consider moving a baseball 90 miles an hour versus pushing a car 90 miles an hour. There's a very big difference there. The velocity is the same, and accelerating the ball is going to, or the acceleration of the objects are the same if we're going to get it to 90 miles per hour. However, the mass of the baseball is much smaller than that of the car, so the amount of force that is going to be required to move the baseball 90 miles an hour is much less than the force that is going to be required to move the car 90 miles an hour. Acceleration of an object is equal to the force divided by the mass, and we can rearrange this equation to get a classic equation of F equals ma. Now, we use force, we use a unit that is known as a Newton, which is equal to kilograms times meters over seconds squared. So again, think about mass times acceleration. You know that mass of objects in physics class are measured in kilograms, and acceleration is meters per second squared. So the unit kind of makes sense. A Newton is roughly 0.25 pounds, if that really helps you kind of visualize or think about how much force is involved in a Newton itself. An 1,800 kilogram car has an acceleration of 3.8 meters per second squared. What is the force acting upon the car? Well, we know that F equals ma. So we can figure out the force by just simply plugging in the variables here. Your mass is 1,800 times your acceleration. We just simply plug into our calculator and solve. And what we get is a force that is equal to 6,840, and don't forget your unit there, newtons. So again, a very straightforward problem to go through and solve, but again, an important one for us to be able to know how to calculate. Let's move on. Newton's second law also applies to net force. So imagine a rugby scrum, and I don't know how familiar you are with rugby, but watch it. It's like football without pads, and nobody really cares if the other players get hurt. Where they're all trying to push all directions and try to move the ball. Now, the sum of all the force vectors is equal to the net force of the sum of the scrum. Now, this ends up being a vector equation which can have x and y components. So, for example, the force in the x direction is equal to the mass times the acceleration in the x direction. And same with y. The force in the y direction is equal to the mass times the acceleration in the y direction. So we can use vectors to be able to think about how these particular forces are applied here. So if we take a look at the image on the right here, you have two people pushing a box with 40 newtons and 30 newtons going in the same x direction. So therefore, the total force is the sum of the individual forces. You remember that from vectors. So as a result, we get 70 newtons as our net force. The two individuals on the second image are pushing the box in opposite directions. Again, still one with 40 newtons and one with 30. But the net force is going to the right side with 10 newtons. And then if we were to have one person pushing the box from the left and one person pushing from the bottom, well, now that again becomes a vector problem that we can use Pythagorean theorem to solve. The net force of 40 going to the right and the net force of 30 going up results in a net force of 50 going in the upper right-hand direction. So again, we can use those concepts that are directly related to the vectors in order to be able to calculate and solve for a variety of problems. So let's talk about Mo, Larry, and Curly. They're pushing a 752 kilogram boat that floats next to a dock. They each exert 80.5 Newton force parallel to the dock. What is the boat's acceleration if they all push in the same direction? So let's start with there. We want to know the boat's acceleration if they all push in the same direction. Well, we have a boat that has a mass of 752 kilograms. They're all pushing the boat the same direction. So we've got Mo, Larry, and Curly all pushing the boat the same direction. Let's just say to the right. Well, the total force that they're pushing is going to be equal to the individual forces added together. So there are three of them. So if we multiply that by 3, we get our total net force, which is 241.5 newtons. Well, if I know the force and I know the mass, I can calculate the acceleration. Force equals mass times acceleration. Divide on both sides and solve for acceleration. What we get is 0.321 meters per second squared, which is our acceleration, and because it is a positive value, we're going to the right. Again, we established that in the very beginning part of our problem. Now, the second part is asking us, what is the boat's acceleration if Larry and Curly push opposite the direction of Mo? So in this instance, our mass is still the same. But in this instance, we're not going to have our net force that way. We've got two forces going to the right. We got one force going to the right, Mo, and Larry and Curly are pushing the opposite direction. So rather than adding all of our forces together, we're actually going to take our first force, Mo's, but we're going to subtract the force of Larry and Curly because they're pushing in the opposite direction. Remember that force is a function of vectors. So what we get is a total net force of negative 80.5. And we can plug that into F equals ma. So 80.5 equals our mass times our acceleration. We plug those numbers in and we get our acceleration to be negative 1.07 meters per second squared. And again, because that value is negative, the acceleration is actually going to the left, which makes sense because you have a net force greater going to the left than you do to the right. Okay? So again, just keep in mind that forces, we can utilize those as vectors in order to be able to solve for problems in terms of mass and acceleration and force. So nature never really produces just one force at a time. It just doesn't really happen. Forces always come in pairs. For example, you can't really touch someone without being touched in return. In addition, the forces in a pair are equal in magnitude and opposite in direction and act on different objects. So those are a couple of key things we need to keep in mind. For every force acting on an object, there is a reaction force acting on a different object. The action and reaction forces are equal in magnitude and opposite in direction. Now, an important part of the third law, and that concept that action and reaction forces act differently on different objects, is very important. It doesn't mean that anytime two forces act upon each other, it's always a stalemate in terms of movement of direction. We know that we can overcome certain forces based on the different object that we are looking at. Let's do a problem. Two groups of canoeists meet in the middle of a lake. After a brief visit, a person in canoe 1 pushed on canoe 2 with a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is 150 kilograms, and the mass of canoe 2 and its occupants are 250 kilograms. What is the acceleration of each canoe? Well, again, we're focusing on force as a function of mass and acceleration. The key thing to keep in mind here is that canoe 1 pushed on canoe 2 with the force of 46 newtons. So if I push on canoe 2, then it's pretty straightforward here. We'll have 46 newtons as the force. The mass is 250, and my acceleration is unknown, and I can solve for that very easily. With 1, though, remember Newton's third law, right? For every force, there's going to be an opposite force of equal magnitude and opposite in direction. So that means that the force of canoe number 1 is going to be negative 46 newtons. Our mass is 150 kilograms, and our acceleration is unknown. Now it's very easy to plug those into your calculator and solve. For this canoe here, we're going to get negative 0.31 meters per second squared. And again, because it's negative, we're going that direction. And for this one here, on the right-hand side, you get 0.18. That's going in the right direction. Again, that's because we have a positive value here and a negative value there. So again, pretty easy to go through and think about these things. We just have to keep Newton's laws in mind as we go through and do calculations of force equals mass times acceleration. Hopefully by now you've got the learning objectives for this video. You should be able to explain Newton's laws of motion and apply Newton's laws of motion to the concepts related to vector physics. Guys, I appreciate your time. Thank you so much for watching this video. Make sure you like, comment, subscribe, shop merch. This is JLand Bio. Have a great day, and we will see you guys next time. Take care. Bye-bye.